Hello, hello, everyone. Happy Sunday. Thank you so much for joining once again with me. I'm Melissa Maribel here on a Sunday and learning chemistry. So exciting. I'm happy to do this every single Sunday. Leave in a chat. Let me know how you guys are doing in class, where you guys are in class. Leave a comment, everything. I just want to know what's going on with your classes right now. I know everyone is kind of on different subjects. So I want to know what you're on to next. What's the next topic? What you basically need me to teach every single Sunday. So let me know for any suggestions as to what you want me to teach for next Sunday. I also wanted to go over just why I'm even doing this and why I'm doing this every Sunday and committing to it. It's a huge thank you to all of my subscribers. I'm really, really thankful for you guys and grateful for you to actually watch my videos and share them and, give such positive feedback. It's really motivating for myself to just keep going and to keep motivating you guys to keep going as well. So I'm also doing a possible 8-hour session if we get to 10,000 subscribers. So if you guys help me get to 10,000 subscribers, I will be doing an 8-hour live tutoring session for you guys before your finals. Definitely help me out with that, and I will be so happy to do that 8-hour live session for you guys. So today we're going to be focusing on gas laws and gas stoichiometry and just all of the little in-betweens that we have, all of these different, constants and formulas that we have to see. And let's dive right in. So let's focus our screen and look at this. And we'll look at all the different possible gas laws that you guys will notice. And just to even know what a gas law is, what it's describing, it's pretty much describing how different properties are relating to one another. So let's say, how pressure relates to volume or how pressure relates to temperature or moles or whatnot. So that's really essentially all we're really talking about with gas laws is seeing how a gas will behave or act when it's put under different conditions, or, if we change the pressure, if we change the volume, and so on. And there are several different types of gas laws, as you guys may already know. We'll be focusing on these main 6 today. And then towards the end, we also will be doing some gas stoichiometry. And also for ideal gas laws, we will also be getting into how to calculate molar mass and the density of a gas as a whole. So if you're waiting for something like that, that's going to be towards the end. So the first one that we're going to focus on is going to be Boyle's law. And Boyle's law will compare pressure and volume. And how they relate is they are inversely proportional. And by the way, this is the only time that you will see one of these laws being inversely proportional, meaning as one goes up, the other one goes down. Everything thereafter would then go hand in hand or be proportional, meaning it will go, like, let's say one increases, then the other one will also increase. So in our case for Boyle's law, as we increase the pressure, we're actually going to decrease the volume. And I have a little image here. I'll explain what this even is talking about. So looking at those little aqua dots or polka dots, as I tend to love, those are really just your gases. Okay, I'm just trying to kind of simulate these gas particles that are floating around. And what's happening is if we have some sort of fixed volume for at least this first one, there's not too much pressure. So looking here, there's not too much pressure. The gases are freely just moving and they don't want to be right next to each other. So they're kind of spaced out. So there's not too much pressure. If I were to kind of shrink that volume and really just start to kind of compress it down, then there's going to be more pressure because the gas particles have nowhere else to go but towards each other. And then that's what adds that extra pressure. So that's what we're talking about when we increase the pressure, we decrease the volume. All right, so this is Boyle's law, where it's P1 times your V1 is equal to P2 times your V2. And let's try a question. All right, so our first question is a cylinder equipped with a movable piston has a volume of 7.25 liters under an applied pressure of 4.52 atmospheres. What is the volume of the cylinder if we decrease the applied pressure to 1.21 atmospheres? All right, so we are only comparing volume and pressure. So then that has to have been Boyle's law. And I'm just going to write down everything that we're given. So the first thing that we are given, it says a volume of 7.25. So that will act as our V1, so 7.25 liters. Then our first pressure will be that 4.52 atmospheres. And lastly, and the next it's telling us what is the volume. So we're looking for V2, so we don't know what V2 is. And then next, if we decrease the applied pressure, so it's P2, which is right here, 1.21 atmospheres. And then typically, if you aren't sure, you know, which one's V1, which one's P1 and whatnot, typically the first sentence will give you your initial volume or temperature or pressure or whatever you're looking for. And then towards the end, you'll get the final. I don't want to say that's always the case. It really just depends on the question. But typically I see the initial values in the first sentence. All right, moving on. Let's plug it into the formula. The nice thing about these gas laws is once you know the formula, you literally just plug in and you're done. Now, let's go ahead and plug in, and then just looking at this, we'll have 4.52 atmospheres times our V1, which was the 7.25 liters, right? This is P1 times V1 is equal to P2 times V2. So P2 would then give us 1.21 atmospheres, and we'll multiply by V2 because that's what we're solving for. I'm going to multiply these two values together. So 4.52 times 7.25 will give us 32.77. And then for now, I'm just going to show that we have atmospheres times liters because we can't combine those. We can't really do anything with them, just put them together really. And then I'm going to divide over the pressure and solve for the volume. So dividing this over, we'll get 1.21, 1.21, dividing those cancel. And we are dividing atmospheres, so the atmospheres will then cancel. And we will be left with liters, since that's what we're solving for. So our answer would have been 27.0826 liters for V2. Let's go back and determine how many sig figs we need to round to. So all of our givens were 3 significant figures, so we'll round to 3 sig figs. So rounding to 3 sig figs, I'm going to stop right here and look and round up because there's an 8 there, so that our final volume would have been 27.1 liters. That's our answer for that first question. So that was using Boyle's law. Let's continue on just down the road and just moving along with all these different types of laws that we'll see. The next one will be Charles' law. With my little image, we'll go over what I'm trying to explain there. So Charles' law is going to relate volume and temperature. And as I mentioned now, Boyle's law was the only one that really had that inversely proportional relationship, meaning as one goes up, the other one goes down. Now everything thereafter will, as they both increase or decrease. Like that's kind of like the concept here is like Charles' law, the volume will increase, then our temperature will also increase. So that's what we're going to keep saying is every other law accordingly will now be proportional. So looking here as our volume, so I'm going to show that this little figure right here, let's pretend that's a container. Okay, use our imagination for a little bit. So if this is some sort of small container, it's not going to require too much heat. So I didn't put too much heat. So as I have a good amount of temperature and a small enough of a volume, that's it. They're proportional to each other. However, if I were to get a larger container, I would need more heat to warm up that container. So then that's where the volume and the temperature go hand in hand as we then increase our temperature, actually even increase our volume, we have to increase the temperature because we have more volume, right, to heat that up. So that's how it goes hand in hand. And then this is our specific formula that we'll see. V1 divided by T1 is equal to V2 divided by T2. Side note, and a very, very important note, is whenever you are doing any sort of gas law involving temperature, temperature has to be in Kelvin. I'm going to say that again. Temperature has to be in Kelvin for every single gas law. No exceptions for that. All right. So definitely keep that in mind every time, or else your answer will be wrong. Okay. And then just remember how to get the typical thing that you'll see is going from Celsius to Kelvin, we add 273. And we'll see that a lot with these next questions. So let's try one. All right, our first question. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? All right, so let's just start seeing what we're comparing. We first have our initial volume, which is given. So our initial volume is that 88.2 milliliters. And then our first temperature is the 35 degrees Celsius. And remember, we do have to convert that. We'll convert that in a second. And then it's going to a final temperature of 155 degrees Celsius. And it says, what is the final temperature? So, or volume, I'm sorry. So we're looking for V2 in milliliters. So we're looking for V2 specifically in milliliters. Let's go ahead and first just start off with converting our temperature to Kelvin. So I'm going to add 273, and go from there. This gives us 308 Kelvin. Now it's in the proper unit. And I'll convert the other one as well. So 155 plus 273 will give us 428 Kelvin. Okay, let's set it up. So using Charles' law, let's put our volume on top, the 88.2 milliliters over T1, which is 308 Kelvin, divided by V2. We don't know what V2 is just yet. That's what we're solving for. And divided by 428 Kelvin. All right. So with this sort of example, I just like to cross multiply. So doing this, I'll do V2 times 308. So it'll give us 308 V2. And then multiplying across as well, I'll multiply the 88.2 milliliters times 428 Kelvin. All right. And then there was a milliliter. Actually, there was a Kelvin right here. So 308 Kelvin. I don't typically write the unit when I'm actually plugging it into the formula, but just to show you how everything's going to cancel, that's what I'm doing right now. The reason why I don't typically write the unit, it makes it a little bit more confusing or just adds more to the, to the numbers in general. As long as you know what you're solving for, then you should know what unit it should be. But for now, let's just kind of practice still having those units, seeing how they cancel and whatnot. So let's multiply. So 88.2 times 428, that'll give us a very large number. And we still have milliliters Kelvin. And that will equal 308 Kelvin times V2. Next step is to divide over that 308 Kelvin to cancel so we can solve for V2. And you'll notice that the Kelvin will cancel and we will be left with milliliters, which is what the question asked for, the volume in milliliters. And then we'll divide this by 308. And our V2 is equal to 122.56 milliliters. Let's check our sig figs and see what we should round to. All right, so I'm going to round to 3 sig figs. So having this round up, this would have been 123 milliliters. So as I mentioned with a lot of these questions, it's really just identifying what you're comparing. So in our case, when we see that, okay, in this question, we're comparing volume and temperature, what's the only formula that involves volume and temperature has to be Charles' law. And then we'll look at another question and let's say, okay, we're only comparing pressure and volume. So pressure and volume, that has to be Boyle's law. So essentially, I know a lot of times students feel like, where do I start? What formula do I use? What is going on? So I just want you to start off with writing what you're given. And once you notice like the numbers that you're actually given, are you given pressure or volume? Then it's just easy from there to figure out what formula you're using and continue along with the problem. So let's see another type of gas law. Avogadro's law. Avogadro's law is now relating volume and moles. So right here I have a little balloon, different sizes and balloons. So the concept here is as we increase the volume, we will increase the moles, or increase the moles, increase the volume. They're once again proportional to each other. So I want you to think of you're blowing up a balloon and it starts off very small. So you're not really, let's say if we're, us physically actually blowing up the balloon, as we start to kind of breathe or, put air into the balloon, there's not too many moles of air in the very, very beginning when we're just starting to inflate the balloon. So that's why it's very small. So our volume is very small. Yet once we continuously, keep on blowing up that balloon and it starts to get larger and larger, then the volume is a lot larger because we placed more moles of air into the balloon. So it makes sense why they go hand in hand overall. And this is an image for you to kind of understand that the dots just represent the gases, how many moles we have as a whole. Now, Avogadro's law will be our volume, our V1 divided by N1, and is equal to V2 divided by N2. Since there is no temperature, there's no reason to convert any sort of units whatsoever, which is nice. And we will try another question. All right, so our next question, a 4.65 liter sample of helium gas contains 0.225 moles of helium. How many additional moles of helium gas must we add to the sample to obtain a volume of 6.48 liters? Assume constant pressure and temperature. So this is very important to note. I've oftentimes seen questions that say this gas is at constant pressure, constant volume, constant temperature. If anything says constant blank, that means we are not using it. It's irrelevant. It's there to possibly trick you a little bit, or it's kind of like a hint just saying you don't use pressure, you don't use temperature whatsoever. So definitely look out for that. Whenever it says assume constant pressure or temperature, that just means you're not using it. You're not using pressure or temperature. All right. So now looking at this, let's just identify everything that we're given and what we are comparing. So our first thing here, we have liters, that's a volume. So our first volume is that 4.65 liters. Now our moles, our first moles are given. So the 0.225 moles of helium. And it's saying how many additional moles of helium, meaning we're solving for N2 or the second amount of moles. So we don't know how many moles there are. And then lastly, it gives us to obtain a volume of 6.48 liters. That is our second volume. Plug it into the formula. So plugging this into the formula, V1 is on top, 4.65 liters, divided by N1, 0.225 moles. And that's equal to V2, so 6.48 liters, and then N2. We'll cross multiply once again. So I'm going to multiply the N2 times that 4.65, which really gives us 4.65. I'll leave the liters there for now, times our N2 is then equal to, and let's cross multiply the others. So now we will multiply 0.225 moles times 6.48 liters. Let's see what that gives us. So 0.225 times 6.48. And that'll give us 1.458 moles times liters is equal to 4.65 liters of N2, or times N2. And then I'm going to divide both by the liters, so that unit will then cancel out and give us moles. So those liters, as we see, they cancel, and then we'll get moles, which is what we're looking for. So 1.45, and then divide that by 4.65, and this will give us N2 is equal to 0.31354 moles. Check out how many sig figs we're rounding to. Let's see. So going back to our given, we have 3 sig figs for absolutely everything, right? Remember that leading zeros don't count. So in our case, we'll round this to 3 sig figs. So I'm going to stop here and look to the 5, and that's going to round up. So our answer is 0.314 moles of helium. Let's keep going. There's so many more, I know. All right, next little image that I got for you, next other type of gas law that you'll see. So this is Gay-Lussac's law. Now, this is comparing pressure and temperature. And as you can tell, I have like a tea kettle, and I want you to imagine that that tea kettle is on a stove. Okay, so first off, if I just put a tea kettle on the stove and I don't really turn up the heat too much, so there's not much of not much temperature right now, not much heat. And in that case, there's not much pressure because nothing is really, the gas particles aren't really kind of moving too quickly. So now, once I increase the temperature as a whole, that's why you hear the tea kettle start to really scream, right? I think a lot of us have heard that sound before, and it's freaked me out before. But that's kind of the concept. And what's happening is that tea kettle it has so much pressure inside that it starts to scream or let out that steam as a whole. So that's the concept here, is as we increase our pressure, we also increase our temperature, and vice versa. So if we increase the temperature on that tea kettle, our pressure then starts to go crazy, right? It starts to increase as well. So that's the concept behind this law. And then now looking at this, our overall formula would be P1 divided by T1 is equal to P2 divided by T2. All right, so we are comparing temperature in this case. So we have to convert everything to Kelvin. I'm going to keep saying that. All right, that's so important. I've seen a lot of students make that mistake, and they understand everything else, but it's just that simple thing of always converting your temperature to Kelvin. And we'll keep saying that. So let's try one. Our next example: determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. All right, so do we see a little common hint right there? That constant volume. So constant volume, remember what that meant. It means we don't use it. We don't use volume whatsoever, okay? So definitely know that hint, know that trick. Anything that's saying constant volume, constant fill in the blank, we don't use that, okay? It's not involved in our given or in our problem whatsoever. So in our case, what we're comparing is we're trying to figure out our P2, or our change in pressure. So they first give us 1 atmosphere. By the way, pressure is measured in a lot of different things. The most common one is atmospheres. I will also give you like a table as to what the different types of pressure units that you will see, just because you haven't seen them just yet, and all these different conversion factors, just to also know, unfortunately. And then continuing on with this, so our first pressure would be 1 atmosphere. And then our first temperature in Celsius, which we have to convert, is 20 degrees Celsius. We're solving 20 point. You know what? Let's write this in the proper sig fig notation just because we will have to go back and figure out how many sig figs we have to round to. So, and then pressure is what we're solving for. And then T2 is the 30.0 degrees Celsius. First step, convert all of your temperatures to Kelvin. So we'll add 273 to each one of these. And then we'll get 293 Kelvin. And then we'll get 303 Kelvin. Okay, set it up. So putting our P1 on top is that 1.00 atmospheres divided by T1, which is 293 Kelvin. And that's equal to P2, which we're solving for, divided by 303 Kelvin. Cross multiply. So cross multiplying, we will get 293 Kelvin times P2. And that's equal to 1 times 303. So really it's just 303 atmospheres Kelvin. Divide and solve for P2. So dividing this over 293 Kelvin on either side, those then cancel, our Kelvin cancel, and we are just left with atmospheres, which is what we're solving for. So let's see what we get. So 303 divided by 293. And our pressure is 1.03 atmospheres. And let's double check if 3 sig figs is correct. And it is, right? All of these zeros do count. So 3 sig figs is what we round to. Okay. Next type is going to combine pretty much the majority of all of the laws. The only one that the combined gas law does not include is Avogadro's law, and that's because there's no moles in this law as a whole. It really combines all of the other previous laws that we've seen before. So it will combine. It combines Charles' law, and then it also combines, and here I'll show you. So it combines Charles' law with the volume and temperature being divided and being compared. And then it also combines P times that V, which was that initial one, right? That was Boyle's. And it also combines the last one that we just talked about. So pressure and temperature. So Gay-Lussac's law is also in there as well. So that's pretty much the concept of combined gas law. Just literally combine a bunch of gas laws together. It says it in the name. So this is a really, really important one to know. I've seen this question a lot as well. And another thing to kind of just mention is sometimes you'll get, like, this is actually an easier one to spot because they give you so much information. So once you see that, like once you're writing all your givens and you have, oh wait, I have 2 volumes, I have 2 pressures, I have 2 temperatures or whatnot, then that's your hint to kind of tell you, oh wait, if I have all of this information, I am comparing pressure, volume, and temperature, and I have multiple of them, then I do use the combined gas law. So that's a nice little one to kind of just notice, and we'll see that in a second. All right, so let's start off with looking at this first question. A gas takes up a volume of 17 liters, has a pressure of 2.3 atmospheres and a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin and lower the pressure to 1.5 atmospheres, what is the new volume of the gas? So as I mentioned, you're going to see just an overload of information, and that's going to hint at using the combined gas law. So we'll see in the very first sentence, it gives us our initial values. So it gives us our initial volume, so 17. So our initial volume is 17 liters. And then it also gives us our initial pressure, that 2.3 atmospheres, and our initial temperature, which is 299 Kelvin. Next, it's going to say, raising the temperature to 350, then that's our second temperature. So that's 350 Kelvin. Luckily, this one's already converted to Kelvin. How nice. And the next one is we're going to lower the pressure. So that's our change in pressure. So 1.5 atmospheres. Saying what is the new volume? So the only one that's left is V2. So that must be what we're solving for. Plug it all in. So plugging this all in, no need to change any sort of units whatsoever since temperature is in Kelvin. I'm going to plug in that 2.3 atmospheres, multiply that by the volume, so 17 liters, and then divide that by T1, which is 299 Kelvin. Set that equal to P2, which is 1.5 atmospheres. Multiply that by V2, which we're solving for, so I'm going to leave that just as V2, and divide that by our second temperature. And so far, that's what we got. Let's multiply, divide. So I'm going to start off with just multiplying these two values. So 2.3 times 17. We'll get 39.1, and I'll leave the units atmospheres times liters, and then divided by that temperature. So we have two options as to how to approach this question algebraically. So what I tend to do with these types of questions is I just automatically divide. So after I've multiplied those two values together, I then just divide these two. And then it just makes it a lot easier. I prefer that method. The other way that you could have done was you could have just cross multiplied. I kind of don't really recommend that one too much. There's a lot of different factors and things that you have to notice here, but I would just recommend dividing everything right down right away, pretty much. So in our case, let's divide this and see, we'll get 0.13076 is equal to, so let's divide that 1.5 divided by 350, and we'll get 0.004285. And notice that I'm not rounding just yet. I just wait at the very, very end to round to really, really get something that's as accurate as I can see. So in our case, our last step would then be dividing by the 0.004285, and we'll see what our new volume is. So 0.13076 divided by 0.004285, and our volume is 30.5 liters. Okay, so not too bad. Let me just double check our sig figs to make sure that that was it. And nope, two sig figs, right? 17 and 1.5, that's our lowest. So let me go back and round this up. Let's round this up to 31 liters. Just because sig figs are important. They always are, I know. Never goes away. The next one is probably the most important law that you have to know. Okay, this is going to keep popping up over and over again and again in chemistry. So in our case, it's called the ideal gas law. And I want you to think of this as when we say ideal, that is the chemistry lingo for saying a gas will behave perfectly or ideally under a certain set of conditions. So that's kind of the concept behind the ideal gas law. And we're going to get into different types of conditions that we'll see that gases, do behave well or whatnot. It's called STP, and we're going to get to that very, very soon. Now, what I've boxed here are the different types of units that you for sure have to know. So in the gray, you will see those are the different pressure units as a whole that you can see. So we'll have pascals and kilopascals, millimeters mercury, torr, psi. So those are all different types of units for pressure as a whole. I know you probably aren't familiar with those just yet, but I did want to kind of mention that because you will see at least the most common ones that you'll see, by the way, would be torr, millimeters mercury, and atmospheres. So those for sure are the most common. Everything thereafter, you don't really see too often, depending on your professor or teacher or, textbook or whatnot. But everything then equals 1 atmosphere. This is what we're going to be using to convert our units. The nice one that I would say I personally like, because it makes it easier, is since millimeters mercury and torr are the most common ones, luckily they both equal the same conversion factor or the same numbers, so don't really have to think much from it. So cool. And then now the other thing to really mention here are units for ideal gas law. Okay, so everything else we were saying it's fine, you don't have to convert anything else besides temperature. Now we do. So now the pressure has to be in atmospheres. The volume has to be in liters. N will be in moles. And R is known as our gas constant. So that's typically given to you on exams, depending on your teacher or professor. And our gas constant, you'll see there's going to be variations, by the way. There's going to be a variation. It could be 0.0821. Some people round up. Others leave it more exact with 0.08206. And our units are liters times our atmospheres and moles divided by Kelvin. Okay, so now, and also, by the way, your temperatures in Kelvin, which we really knew that. Now, the reason why the ideal gas law has to be these units is take a look at your gas law, your gas constant, and you'll see that those actually are all the different units that we just described. So it works out so nicely that when you use your gas law, whatever you're solving for, like let's say if you're solving for pressure, then our liters, our moles, and our Kelvin would all cancel out because everything's in the appropriate unit. So that's why we have to get it down to that specific unit for pressure, volume, moles, and temperature. All right, so that's a side note. Know that, and definitely know these different conversion factors as well. Our ideal gas law is PV equals nRT. You will keep using this a lot, so much. It doesn't go away. All right. Let's try one. So what volume does 0.556 moles of gas occupy at a pressure of 715 millimeters mercury and a temperature of 58 degrees Celsius? So let's identify what we're solving for. We are asked to find volume. So it says, what volume does 0.556 moles? So that's our N, since that's our moles. Now it tells us our pressure, which is not in the unit, right? It has to be in atmospheres. So we will have to convert that in a second. And then now we said we're solving for volume, and we have our temperature as well, 58 degrees Celsius. For PV equals nRT, first step is check if all of your units are in the proper unit, which they're not. So in our case, let's go ahead and convert that pressure. So converting that pressure, we'll put the millimeters mercury on the bottom so they can cancel, and atmospheres on top so we can get to atmospheres. Our conversion factor was 1 atmosphere per every 760 torr. That's our millimeters mercury. That's our other one. Now we'll divide those two values. 715 divided by 760. And our new atmospheres for pressure is 0.94 atmospheres. Next step is to convert our temperature to Kelvin. So add 273. That gives us 331 Kelvin. Plug it into your formula. So plugging this in, by the way, some students prefer, instead of just plugging everything in and then dividing to solve for what you have, like V, some students prefer to actually manipulate this formula right off the bat and solve for volume. So I'll show you either way. So if you wanted to solve for volume just for this formula as a whole, to get V by itself, P is being multiplied. So we want to do the opposite operation to cancel it. So we'll divide by P, and that cancels out your pressure. And now you're left with just V is equal to nRT divided by P, and then you can just literally plug in. I'll show you both methods, and you can decide whichever you find easier. So for this first one, Here, let me put the other formula. So for this first one, I'm just going to literally plug in everything that we're given. So if our volume is equal to the moles times our gas constant, so that's 0.08206 liters atmospheres divided by moles Kelvin. And then lastly, our temperature, 331 Kelvin, all divided by pressure, 0.94 atmospheres. And let's look back at that unit and see how everything does cancel. So our moles would cancel, our Kelvin would cancel, and our atmospheres would cancel. And since we're solving for volume, our liters is the only thing that remains, which it worked out perfectly. It will work out perfectly every single time if your units are correct. So now let's multiply just all of these values on your numerator. Let's see what we get. 15.109 divided by 0.94. And then our volume is 16.065 liters. Let's see how many sig figs we have to round to. So we have 3 sig figs as a whole. So I'll round this to 3 sig figs, so 16.1 liters for our volume. And let's see how that would have worked out if we would have just used the typical format of PV equals nRT. So if we didn't know what our volume was, I'm going to just leave it. So I'll plug in all of the values that we do know, and then we'll solve for V from there. So our first step would have been plugging in pressure, so that's 0.94. And then volume is equal to our moles, which was at 0.556 times N, 0.8206 times our temperature. Running out of room. So 331. And then it would be the same exact thing, really, because we'd multiply straight across. That would give us that 15.10199. And then lastly, to solve for V, you would just divide by the pressure. Those cancel, and it will give us the same exact answer. So it doesn't matter which way you choose. They're both going to give you the same thing. I personally, it really depends on, how much time I'm given. If you prefer this method where you first start off with solving for your volume or whatever you're actually solving for just based on the question, it does make it easier to just plug in and then plug it into your calculator. Or if you're not too sure about that, maybe algebra isn't your strong suit, then I recommend just plugging it into the formula and then solving from there. All right, so the next concept is going to be STP. So as I mentioned, there are certain conditions that ideal gas laws, or really gases as a whole, will behave ideally. That was just our chemistry lingo once again, as saying, in a perfect world, we have these gases that are behaving perfectly or ideally. So these are a certain set of conditions, or just, it's called STP, that it really behaves ideally or perfectly, the gases do. So in our case, STP, or standard temperature and pressure, is a certain set of units or a certain set of fixed numbers that we really know. So STP is 1 atmosphere for our pressure. Temperature is 273 Kelvin, and our volume is 22.4 liters per mole. That one is very, very important, I would say, that last one especially. So a lot of times STP is used, will be used with the combined gas law. And we'll see that in a second, just how that all works together. So definitely know what STP stands for and what it means, like with all of these units. This is very, very important to note as well. Okay. That being said, let's see how STP works with a question using the combined gas law. So in our case, we're going to see a question that says a gas occupies 256 milliliters at 720 torr and 25 degrees Celsius. What will its volume be at STP? So STP, as we just saw, gave us pressure, temperature, and volume. STP in this type of question, and most of these questions, will act as our initial volumes. So our initial amounts, really. So in our case, we would have P1 and T1, not V1 because we're actually given that. Yes. So it will be at STP. So essentially, actually, I think this is a different question, but typically they give you the initial pressure and temperature. That's what you typically use. But let's double check this question one more time. Just looking at it, let's see what they're giving us before getting to that. So a gas occupies 256 milliliters at 72 degrees or 720 torr and 25 degrees Celsius. What will its volume be at STP? This one's actually a tiny bit different. So typically at STP, they give you the initial pressure and temperature. That's kind of something to note. So what I want you to get from STP and get from like a question like this is if you feel like there's not enough information to solve for this, where you saw that, sure, this is our volume, this is our pressure, this is our temperature, and we're asked to find volume. Wait, where are the missing, pressure and temperature? Then right then and there, you can say, well, we have to use STP. So P1 then had to have been, or one pressure had to have been 1 atmosphere, and the temperature had to have been 273 Kelvin. So it's just an extra little thing to know to help you identify these types of questions or fill in the blanks of these questions, really. So continuing with this, our volume that's given is 256 milliliters. So in our case, we will get our V1 in our case will be 256 milliliters. And our first pressure is 720 torr, which we have to convert. Actually, no, we don't have to convert. So this one we don't have to convert because it's not PV equals nRT, meaning we're not doing ideal gas law. So never mind. That's why I said we had to convert. We do have to convert because our pressure at STP is 1 atmosphere. We can't plug in torr and atmosphere in the same question. So you do have to convert those torr down to atmospheres. So I'll plug in that 260 torr per every 1 atmosphere, divide those values. So 720 divided by 760. Let's see what that gives us. 0.947 atmospheres. And then we will also have, let's see, our T1 is also given. So that 25 degrees Celsius is given. Let's convert that to Kelvin. So add 273. We'll get 298 Kelvin. And then we have our T2. That's 273 Kelvin because that was our STP value. And then lastly, we're just solving for V2. So we'll plug in all these values into our combined gas law again and go from there. So in our case, we'll see that P1 was what we just converted into atmospheres, and then times our volume, our V1 was 256. And then our divided by our temperature, so 298 Kelvin. And P2 was just 1 atmosphere. V2 is what we're solving for. And 273 is our next temperature. So I'm going to start off with just multiplying these two values. 242. That just glitched. 242.432 divided by 298. And then 1 times V2 is really 1. So divided by 273. And then from there, I'll still leave the 1 there just to show. And then from here, I'm just going to divide these two values. I will also divide 1 divided by 273. This would give us 0.81353 is equal to, so 1 divided by 273. That gives us 0.00366 V2. And we'll solve for V2 by dividing both sides by this amount. And those would then cancel. And 0.813353 divided by, we just got, so we'll have a volume of 222 milliliters. And that makes sense. Our initial volume was 256 milliliters. So yes, that's fine. 222. That just means it went down. All right. So why don't we get to some gas stoichiometry? And we will be using multiple ratios. Okay. So getting to gas stoichiometry, it's really not too bad, I'd say. It's just knowing what you're given again and what you're solving for as a whole. So that's what we're going to identify first in this question, what we're given, what we're solving for, and build a plan from there as to get to what we want to find. So in our case, let's see, we have what volume of O2 is, so right then and there, what volume of O2. So we're going to find O2, the volume of O2 is produced when 28.5 grams of hydrogen peroxide decomposes to form water and oxygen at 150 degrees Celsius and 2.0 atmospheres. So let's see what we're given. So it says they give us 28.5 grams of hydrogen peroxide and to form water and O2 at some sort of temperature at 150 Celsius, which we will convert to Kelvin, and then pressure is 1 atmosphere. Okay. So we must be using the ideal gas law because we are given grams, which we can change to moles. We are given temperature and pressure, and we're asked to solve for volume. So the only one that does have pretty much all of those values is the ideal gas law. And before we start to just plug in, we have to make sure all the units are correct, as well as we don't have the proper compound. So by me saying that, I mean we only have grams of hydrogen peroxide. We want the volume of a completely different compound, right? We want O2. So because we don't have the proper compound, we first have to do a moles-to-mole ratio, because a moles-to-mole ratio is what we use when we're trying to change our compounds as a whole. So in our case, you'll see the first step is to convert our grams of hydrogen peroxide to moles of hydrogen peroxide. And then we will use this nicely balanced equation to get to moles of O2. We have to do that in the very, very first step before we use the ideal gas law. So in our case, let's do 28.5 grams of H2O2. And then we'll place the molar mass because we're getting to moles, right? So remember that this part was molar mass, that first conversion factor. As we go from grams to moles, use molar mass. As we go moles to moles, when we're changing our compound, we use the mole-to-mole ratio from our balanced equation. So in our case, let's see our molar mass of hydrogen peroxide. So I'm going to let's figure out the molar mass of that. This would have been 2 times 1.01, which is the mass of hydrogen, and 2 times 16, the mass of oxygen. Multiply and add these values together, and we'll see what we get. So we will get 34.02 grams of hydrogen peroxide per every 1 mole. Now we'll get to cancel these grams of hydrogen peroxide and then move on to moles of O2. So I'm going to place the moles across from each other of hydrogen peroxide so they can cancel, and moles of O2 on top. And let's go back to our balanced equation and see how many moles to moles we have. So we have 2 moles of hydrogen peroxide, and there's only 1 mole of O2. So there's 1 mole of O2 and 2 moles of hydrogen peroxide. Let's multiply straight across and divide. And we will get, so let's see, 28.5 divided by 2 times 34.02. And our moles now of O2 is the 0.4188 moles. Not done just yet. So next step for this gas stoichiometry question, we'll go ahead and plug this into PV equals nRT. And I'm going to bring back everything else that we had before. So first step, though, we do have to convert this temperature to Kelvin. So I'm going to add that 273 and go from there. So 150 plus 273 will give us 423 Kelvin. And I'll bring down the pressure that we also had, which is 1 atmosphere. And we're solving for volume. So we do have plenty of information. And remember, your gas constant is at 0.08206 liters atmospheres divided by moles Kelvin. So let's plug it in. So I'm just going to plug everything in right off the bat, where this would have been P is 1. And then we're solving for volume, so we don't know what the volume is. And then our moles is 0.4188. Gas constant is 0.08206. And our temperature is also given. So we just change that to 423 Kelvin. This one's a lot nicer. We're just going to multiply straight across and then divide by 1, which really will just be itself. And we will get 14.537 for our volume. This is in liters. Now let's double check our sig figs as we always have to. So in our case, we will have 3. Actually, no. We will have 2. And I realized, I don't know where I got this one from. It was 2 atmospheres. 2 atmospheres. Sorry about that, guys. So 2 atmospheres. Let me go back and change that then because we're not done. It was 2 atmospheres, not 1. So we'll divide by 2. And we said we're rounding to 2 sig figs because our pressure was 2.0 atmospheres. So dividing this by 2, we'll get 7.268. I'm going to round to 2 sig figs, so rounding this up. So 7.3 liters for our volume. And that's how we do that. So first step, just going back into this for a gas stoichiometry question, is to just focus on what compound you're using. Okay, so they told us what volume of O2, yet they gave us the mass of hydrogen peroxide. So that's why you couldn't have just found the moles of hydrogen peroxide and plugged that into your PV equals nRT formula, because that would have been wrong. That would have then been the volume for just hydrogen peroxide rather than the volume of O2. So double check that, double check what you're given, what compound you're given, and what compound you're trying to find. And that'll help you get to do your stoichiometry or your multimole ratio to actually find what you're looking for. So we have time for maybe one more type. And I wanted to get into calculating, let's do the density of a gas. So calculating density, remember density is mass divided by volume. So keep that in mind for this question. So this question is stating, calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters mercury. Okay, so as I mentioned, density will be our mass divided by our volume. And in our case, for these types of questions, specifically for gas laws, you will have, typically you get, grams per centimeters cubed, or you'll get grams per milliliters for densities. However, for gas laws, you will have something a tiny bit different. You're going to have grams over liters. All right, so keep that in mind. That's the specific unit for density for a gas. Now let's go and identify all of your givens in this question. So in our case, we are given the temperature, 125 degrees Celsius, and our pressure, 755 millimeters mercury, and we're asked to find our density, and density is measured in grams per liter. So we first have to make sure all of our units are correct because we will be using PV equals nRT, or the ideal gas law. So in our case, our units are not okay. So we'll correct them. So I'm going to add the 273 to change that to Kelvin. That's 398 Kelvin. And I'll change this to atmospheres. So 1 atmosphere is equal to 760 millimeters mercury. Divide those. We'll get 0.99 atmospheres. And let's note that we really aren't given much information, right? So we're not given the amount of moles. We're not given the volume. And all we have is pressure and temperature, and we know the gas constant. So whenever you have two unknowns for a density problem, you will solve for N divided by V. So you will solve for N over V, because this will give you your moles divided by your liters. And you're one step closer to getting grams per liter, which is your density. So we'll see that in a second. So I went ahead and solved for PV equals nRT. All you have to do, by the way, is here, I'll show you how to solve for N over V. So PV equals nRT. If we're solving for N over V, we'll divide over RT. Those cancel. Now that's N is equal to PV equals RT. And then we want to get V by itself. So what we can then do is multiply by the reciprocal of V, so 1 over V, because that would then cancel V. And if we do that here, then you get N over V is equal to P divided by RT, which is the formula that we want. So looking at this, now we can plug everything in and go from there. Now that all of our units are correct, let's plug that in. So N divided by V is equal to our pressure, which is 0.99 atmospheres, divided by our R, 0.08206. And let's put our unit. So liters, atmospheres, moles, Kelvin. And then our temperature is the 398 Kelvin. You'll note that all of your units pretty much cancel. So the Kelvin cancel, the atmospheres cancel, and we will then be left with, we actually would be left with moles over liters, just because this is a fraction dividing another fraction. So these would actually flip. So dividing these values out, let's see what we get. We get 0.0304 moles over liters. Not done just yet. So we still want grams per liter. We at least have the liters on the bottom. So what we'll do next is they told us what type of gas it was. They say it's nitrogen gas. So now we will use nitrogen's molar mass to cancel out your moles and get grams. So I'm going to multiply by the molar mass of nitrogen. And note that nitrogen is diatomic. Okay, diatomic means that it exists only in two. So instead of just one nitrogen, that means it would be two. So it would be N2. That's the molar mass that we would be using. So nitrogen, so 2 times 14.01, I believe, and then that's 28.02 grams per mole. Now looking at this, this would be 1 mole on the bottom of N2 and 28.02 grams of N2. Now we will multiply straight across. And we will get our density, because that's 0.852 grams per liter. Note that your units, your moles would cancel, and you're left with grams per liter of N2 gas. That's how we figure out density. All right, we went through a lot today. Thank you for joining in, for being here. For those of you who joined a little bit later or are watching this as a replay, let me know in the comments. Let me know what you want me to focus on. What are the topics that you need help with? It's really just helpful for me to know. I know that everyone's on different levels or different subjects or topics. So I really want to cater to you guys and to help you guys out with as much as possible. So please let me know in the comments, in the chat, what you want me to teach. That's the main thing. So not many tutors are going to be at your disposal like this. So please let me know. And as mentioned before, I will be doing an 8-hour live session if we get to 10,000 subscribers. So please share with your classmates, your friends, teachers, anyone that you feel like would benefit from learning chemistry or needs some help with chemistry. Please share my videos, and I will see you guys next Sunday, and we'll keep posting more and more videos for you guys. And once again, please let me know what you need help with. All right, guys, have a great Sunday.